Hello everyone. Thanks for taking the time to listen in on this presentation. My name is Dave Wright, and I've been working in energy storage since 2010, much of that in the ultracapacitor field. I lead the engineering team at UCAP Power, and today I'd like to give an overview of how ultracapacitors have been used in automotive applications, along with a few areas where we see future potential. Here's the agenda for today's talk. We'll start off by giving an overview of UCAP Power. Then we'll take a look at how automotive electronic trends have evolved over the years. Following that, we'll move into applications, both current and emerging ones. Since it's such an important topic, we'll talk briefly about safety, and we'll conclude by reviewing Maxwell's cell lineup. With that introduction, let's begin. For those of you who aren't familiar with UCAP Power, I'd like to start by giving you some background on our company. As most of you know, Maxwell Technologies was purchased by Tesla in the spring of 2019. Tesla's interest was not in Maxwell's ultracapacitors, but in some underlying technology they wanted to use. They proceeded to wind down much of the ultracapacitor business. Many individuals left Tesla in the ensuing months, and in July, several former Maxwell employees formed UCAP Power to continue the commercialization of ultracapacitor technology. UCAP Power's first product, a 600 farad 15-volt module with integrated charging, was introduced in December of 2020. We're proud to be running in several wind farms across the country and remain committed to that market. To bring the story full circle, in May of 2021, UCAP Power acquired the ultracapacitor business and select assets of Maxwell Technologies back from Tesla. This includes the intellectual property portfolio, product designs, and the entire operation of Maxwell Technologies Korea. For me, having served as the Director of Application Engineering at Maxwell from 2010 to 2014, this was one of those back to the future moments. As one of the first companies to commercialize ultracapacitor technology, Maxwell has shipped over 85 million ultracapacitors into various markets. Our products have been installed in over 95,000 wind turbine pitch control systems, 120,000 heavy-duty trucks, and 7 million automobiles. We have also shipped over 15 million cells to electric grid and industrial power customers. This combined experience provides us with a strong foundation for continued success. From our headquarters in San Diego, the UCAP Power team spans 4 continents, with current sales offices in Latin America and China, and more pending in the Midwest, UK, and Germany. We have a relationship with 2 contract manufacturers, one in Texas and one in Shenzhen, China. And of course, we work hand in hand with our engineering and manufacturing colleagues at Maxwell Technologies Korea, located about 50 kilometers south of Seoul. Okay, now that you know who we are, let's get started and take a look at what's happened in the auto industry in the last 50 years or so. With those introductory comments out of the way, I thought I'd try to paint a picture of how automotive electronics has evolved over my career. Pictured here is a photo of my first car. Well, truthfully, it's not a picture of my specific car, but it is the same year, make, model, and lovely green color. This 1968 Chevelle Malibu was our family car for 6 years, then it got passed on to me when I went away to college. It was equipped with a 327 cubic inch V8, and according to the internet, had a sub 10 second 0 to 60 time. It used a gallon of gas every 10 or 11 miles. And of course, as an 18-year-old, I never exceeded the 55 mile per hour speed limits of the era. So, the total electronic content of my Malibu consisted of one component, an AM radio. That's all. Electronic ignitions didn't show up in GM products until the mid-70s, let alone the plethora of electronic features you find in today's automobiles. Had all the electronics on the car failed, the major impact would have been the inability to listen to the Fifth Dimension's Age of Aquarius. Back then, even if an ultracapacitor had existed, there would have been no reason to put it on an automobile. Fast forward to today. Pictured here is the 2023 Cadillac Lyriq, an all-electric SUV. Some of the features included are a 340 horsepower electric motor providing a 5.7 second 0 to 60 time and a battery pack that can store 102 kilowatt hours of energy. Additionally, full hands-free driving is available on major highways. Add in a large touchscreen, regenerative braking, and a whole host of safety, comfort, and convenience features, and you get a vehicle with electronic complexity relatively typical in today's marketplace. There is significant potential for autocapacitors to play a role in a vehicle like this. The folks at McKinsey & Company have suggested that there are 4 primary drivers affecting the automobile over the next 10 years. As shown here, they are autonomous driving, assuming the technical, regulatory, and acceptance issues are resolved. Electric powertrains, assuming continued decline in battery prices, stricter CO2-driven emission regulations, and getting the average person excited about electric powertrains. Diverse mobility. This is perhaps the most radical proposal. Should it be correct, we will see consumers shift from car ownership to on-demand sharing, particularly in urban areas. Connectivity. This can play out in a couple of ways. There is the whole mobile infotainment stream as a potential revenue source, but over time, the vehicle and traffic control scenarios that many forecast will require vehicles that communicate between each other and with specific infrastructure. I would suggest that these first 2 trends, autonomous driving and electrification, have a high impact on safety. Highly reliable power will be required to enable taking over for the driver and having all vehicle control functions performed electronically. Redundancy and multiple energy storage technologies may be required. How big a deal is this? According to Roland Berger, the semiconductor content of a 2025 battery electric vehicle will be 2.25 times more than a 2019 gasoline-powered car. This block diagram shows the basic structure of the propulsion system in a full battery electric vehicle. Within this architecture, we see a host of electronics represented: inverters, DC-to-DC converters, and battery management systems. Not included in this diagram are the multiple sensors and actuators required for autonomous driving and collision warning avoidance, as well as other safety systems such as airbags. There's a lot going on in vehicles like these. If the electronics don't work or don't have power, bad things can happen in a hurry. Here's a similar diagram for a typical mild hybrid internal combustion vehicle. Even without the full propulsion content of the battery-powered architecture shown previously, there is still a significant amount of performance and safety-critical electronic functionality on this vehicle. This diagram portrays the possibility that each of these primary electronic controllers could be equipped with ultracapacitor-based backup power capability. Lacking that capability, faults in the electric power distribution system, whether the defect or external damage, could render the vehicle uncontrollable. Today's automotive engineers must come up with solutions to ensure power reliability. So whether it's a full electric, hybrid, or conventional gas-powered vehicle, there's a lot of electronic content. Autocapacitor technology has several attributes that the automotive industry finds attractive. In most environments, properly designed autocapacitor systems can be expected to last 8 to 12 years. This means that customers don't have to deal with the periodic hassle and cost of replacement. Less post-consumer waste is generated, and there is more flexibility in packaging locations. Autocapacitors have extremely good low-temperature behavior, particularly when compared to lithium-ion battery systems. No special considerations need to be made to ensure that autocapacitors operate in temperatures well below 0 degrees Fahrenheit, and there are no specific safety considerations for cold temperatures. The bottom line is that cold temperatures are simply no big deal with the technology. Over their operating range, autocapacitors behave essentially like ideal capacitors with internal resistance. This means that monitoring systems can be straightforward and consist primarily of voltage monitoring and balancing. No complex state of charge algorithms or charging algorithms are required. Autocapacitors are known for their high power density, and when used for short-term events, this results in lower mass than with competing technologies. Lower mass also means less mass for mounting hardware. This results in improved fuel economy. With their low internal resistance, autocapacitors typically have high round-trip efficiency, with performance above 90% typically achievable. With less heat to dissipate, cooling requirements are reduced, and once again, fuel economy is improved. The same low internal resistance means that autocapacitors can be charged and discharged very rapidly. Another advantage of using autocapacitors is their abuse tolerance. Nail penetration and cell shorting events typically result in an internal temperature rise of just a few degrees Celsius. No thermal runaway occurs unless uncontrolled charging takes place for excessive time periods. With all of the publicity around fires caused by lithium-ion batteries, autocapacitors stand in contrast as relatively easy to deploy safely. With all of the concern around the world regarding heavy metals and battery mineral supply, the lack of cadmium, lead, cobalt, or lithium in autocapacitors means that supply chains are more stable and recycling disposal is uncomplicated. The bottom line is that in the right applications, autocapacitors provide superior power performance and long life with relatively straightforward design rules. What I'd like to do next is talk about a few high-volume autocapacitor applications that are already on the road. One of the first automotive functions to utilize autocapacitors were start-stop systems. From a cost perspective, these systems provide one of the most effective ways of improving fuel economy in city driving. Although simple in concept, there are a variety of requirements that must be met, including battery life, starter life, and maintaining an adequate system voltage so that headlights don't dim, computers reset, or wipers slow down. A variety of implementations have been pursued, from simply supporting the battery with parallel autocaps to temporarily placing charged cells in series with the battery. Depending on automakers' priorities, different configurations are acceptable. The benefits of using autocapacitors in these systems include faster start times, improved battery life, wide operating temperature range, and improved voltage stability. Finally, the mass savings compared to a secondary lead-acid battery are significant. I'd like to take a few minutes to talk through one of the first high-volume automotive applications of autocapacitors, a start-stop system that debuted in 2011 on the PSA Citroën C4 and the Peugeot 308, pictured here. These compact cars were produced by PSA. The PSA system got very high marks for performance, as it used a belt alternator starter instead of a conventional Bendix starter. The result was a very rapid, smooth, and quiet start when the driver's foot was lifted from the brake pedal. This system was also included in the 2017 European Car of the Year, the Peugeot 3008. In 2019, the PSA Group merged with Fiat Chrysler to form the world's third largest automaker, Stellantis. Following several years of success, the system was also introduced in North America on the 2016 Cadillac ATS and CTS sedans, marking the entry of autocapacitors into the North American luxury vehicle segment. Developed by Continental Automotive in close cooperation with Maxwell Technologies, the voltage stabilization system took a unique approach to eliminating the voltage drop that typically occurs when the starter motor is engaged. Under normal operation, switch K1 is closed and switch K2 is open. The 14-volt power net functions normally, with the generator charging the battery as needed. Meanwhile, a DC to DC converter charges a 2-cell autocapacitor string to approximately 5 volts. When a starting event begins, switch K1 is open and switch K2 closes, placing the 2 autocapacitor cells between system ground and the negative terminal of the battery. This boosts the available voltage for the starting event, keeping the voltage high enough to provide a rapid start and preventing any low voltage related problems with electrical or electronic components. This plot shows a vehicle start without the VSS engaged. Let's note a couple of things. The peak current is approximately 800 amps, and the minimum voltage at that point is about 7 volts. That means the system saw an initial power of about 5.6 kilowatts. The starter dropped out at about 0.75 seconds, which we'll say is the starting time. Now let's take a look at how the VSS impacts this performance. In this plot, we can see that the peak current is approximately 1100 amps, while the voltage dropped to only 10 volts. This results in an initial power of 11 kilowatts, twice that of the previous plot. The result is that the starter drops out in half a second, a 33% improvement. That is a noticeable difference, particularly if you've just taken your foot off the brake to accelerate into traffic. This slide shows the components of the system produced by Continental. In the top left, we see the power electronics and control unit. In the bottom right, we see the autocapacitor module, consisting of two 1200 farad cells in series. This slide shows the location of all the components as mounted in the vehicle. The power electronics and ultracapacitor module are mounted near the firewall, away from any direct heat sources. A separate start-stop controller manages the starter generator and communicates with the VSS power module. This represents one of the most successful automotive applications of ultracapacitors to date, with millions of 1200 farad cells shipped. A second high-volume ultracapacitor application is Maxwell's I-ELOOP. This is a mild hybrid system that was introduced in 2012. It uses a variable voltage alternator to capture some braking energy, storing that energy in an ultracapacitor module. In what I regard as a particularly novel approach, the stored energy is not used to accelerate the car, but is used to supply energy to the 12-volt power bus. This energy would otherwise have to come from the fuel tank, so fuel economy is improved by as much as 10% in stop-and-go. Here is a diagram showing the primary components of the I-ELOOP system. A variable voltage alternator is used to increase engine braking, with the resulting energy being stored in the ultracapacitors. This energy then reaches the 12-volt electrical system via a DC to DC converter. This allows the regenerative braking energy to be used without making the alternator a motor generator. For my third example, I'd like to discuss the use of ultracapacitors to start heavy-duty truck engines. Starting is a pain point for many drivers and fleets. Failure to start can be attributed to many causes, but poor battery performance can be caused by overuse of accessories, frequent stops, or poor battery performance in extreme temperatures. Ultracapacitor-based starting systems can improve starting performance, particularly in cold weather, as shown in the top right-hand plot. As the chemical reactions of a battery slow down with decreasing temperatures, ultracapacitors keep much of their power performance and can make the difference between being on the road or waiting for a roadside service truck to arrive. The lost time and expense due to non-starts is a big deal in the trucking industry, and providing a reliable power source to ensure the engine will turn over has significant value. This slide shows the Maxwell Engine Start Module, or ESM for short. Introduced in 2012, the ESM addressed the pain points mentioned on the previous slide. It was offered in both 12-volt and 24-volt versions and adjusted the output voltage as a function of temperature, thereby providing more power when it gets cold. Capable of fully charging in 15 minutes, it can do a minimum of 3 cranking events on a single charge. With its built-in charger, installation is straightforward and does not require significant modification of the truck. This block diagram of a typical ESM installation shows the ESM with the B+ input connected to the existing vehicle batteries and the S terminal connected directly to the starter solenoid. When the key switch is turned, the starter solenoid closes and draws current directly from the ultracapacitor bank, which has been previously charged. When the engine starts, the onboard charger tops the ultracapacitor bank off in a few minutes so the device is ready for the next start. Early testing of the ESM took place at the Center for Diesel Research, located at the University of Minnesota. The ESM was connected to the starter solenoid of a 14-liter engine. Since the dynamometer was not located in a temperature chamber, dynamometer load was used to simulate the harder cranking that takes place as the temperature drops. This plot shows the ESM providing 7 consecutive starts in less than 2.5 minutes with no additional dynamometer load. Representative of a typical moderate temperature start, this demonstrates that the ESM has sufficient energy to start the engine multiple times without any recharge time. This particular plot shows the same test performed with a dyno load of 335 foot-pounds to simulate the impact of increased friction and oil viscosity at cold temperatures. A cold battery might not even succeed once, but this shows that the ESM successfully started the engine on the second attempt. With those current and historical systems addressed, let's take a look at some of the applications we think might be showing up in future vehicles. The parallel combination of a lead-acid battery with an ultracapacitor module represents one of the easiest ways to include the benefits of ultracapacitors for the starting system. Repeated start-stop cycles place a great deal of stress on a lead-acid battery. It simply doesn't have the charge acceptance to recover quickly, and as a result, its performance can decline. The data in this plot is from a 38 amp-hour AGM battery in parallel with 6 2000 farad cells in series. The test cycle consisted of a 30 amp discharge for 2 seconds, followed by 1000 amp pulse, then 500 amp steady state discharge for 2 seconds, and concluding for 7 seconds with a 25 amp, 14.4 volt constant current, constant voltage recharge. In the top right, note that the autocapacitor battery system, the blue curve, maintained much higher voltages than either the 50 amp hour AGM battery or the 55 amp hour flooded lead acid battery. This would be a significant benefit for start-stop systems that can see this type of pattern in stop-and-go traffic. A second system to discuss is an electrically assisted turbocharger. Turbochargers have grown increasingly popular as engine displacements have been reduced. Automakers continue to work hard to satisfy the car buyer's desire for excellent performance across all ranges of engine RPM. An electrically assisted turbo can increase low-speed torque, as the plot in the top right corner illustrates. This significantly shortens turbo lag, but allows for engine downsizing to obtain fuel economy gains without overly sacrificing performance. However, the electrical demands can be quite significant, requiring a large current for a short time. This high power, low energy requirement is well matched to autocapacitors. The sample diagram shown here uses a DC-to-DC converter to decouple the main electrical system voltage from the turbocharger control. The turbo motor can operate at a nominal 12 volt level or can operate at a higher voltage to achieve the desired power at lower currents. In either case, the autocapacitor array can help supply the initial starting current surge, providing faster acceleration for the short time until the exhaust gases can drive the turbocharger. A third system that can benefit from the use of autocapacitors is the active suspension. In these systems, the required power delivery and absorption periods are very short, but the system works continuously. Autocapacitors are uniquely able to deliver high power in short bursts, but they can also absorb power as needed equally well. This very high cycle environment requires extremely high round-trip efficiency, and autocapacitors are relatively unique in their ability to do that with electrical energy. The block diagram of such a system is very similar to that of the E-Turbo, but the power profile is substantially more demanding. Systems designed around autocapacitors can benefit from the outstanding power density of the autocaps, along with their wide operating temperature range and long life. The low internal resistance of the cells results in lower losses, so less cost and mass is associated with cooling. The final system to discuss is the use of an autocapacitor array to serve as a short-term power source during the transition between a primary DC-to-DC converter and a secondary DC-to-DC converter. As mentioned at the start of my talk, the increasing electronic sophistication of electronically controlled features requires highly reliable power to remain safe, with functional safety requirements frequently being specified. In a battery electric vehicle, much of these functions rely on the 12-volt power system to operate. A primary DC-to-DC converter may fail, and the secondary unit may take time to pick up the slack. Current inquiries from automakers cover a range of power and time requirements, but generally we expect time periods of less than a few seconds. Once again, this is right in the wheelhouse for an effective autocapacitor system. In these systems, the autocapacitor is regarded as a life of the vehicle component. Unlike with batteries, excess energy does not need to be added to reach the required power levels. The relatively straightforward management and monitoring of autocapacitors is an attractive alternative to the complexity of state-of-charge algorithms associated with batteries. In summary, an autocapacitor-based backup power system will have an expected life well beyond that achievable with competing battery technologies. The primary energy storage technology for battery electric vehicles, lithium-ion batteries, has gotten substantial publicity for safety issues, predominantly fire risk. Numerous automakers, device manufacturers, and even aircraft companies have experienced problems with battery fires. The following slides will briefly show that this risk is dramatically reduced when using autocapacitors. The first test, routinely done at Maxwell, is a short circuit test. In this case, a fully charged 3000 farad cell is shorted. Don't try this with a lithium-ion battery. The end result is that the cell is fully discharged in 3 to 5 seconds, and its case temperature rises by approximately 4 degrees C. It is a very benign result, as the cell is highly robust to short-circuit events. The second test, occasionally performed at Maxwell, is to subject the cell to uncontrolled charging, resulting in an overvoltage situation. In this test, the cell is constantly charged with a current of 100 amps, without any regard for overvoltage or overcharge limits. After approximately 6 minutes, the safety vent opens and there is an aerosol emission of electrolyte. When the event has completed, approximately 50% of electrolyte has been lost. The cell case temperature in this case reaches 130 degrees C, but there is no smoke or flame. Due to the release of electrolyte, this would be considered a moderate hazard, but it can be avoided with straightforward overcharge prevention mechanisms. The third test to discuss is one that comes from SAE J2464, and it's the nail penetration test. This is a common test performed on a variety of technologies. In the test, a 3 mm rod is forced through the fully charged cell in a radial direction. A spark igniter is present to ignite any flammable gases that might be released. The results of this test are similar to the short circuit test. The cell case temperature increased by 5 degrees C, but there was no thermal runaway, vapor ignition, flame, or smoke. Once again, this is considered a low hazard level. The fourth and final test, also from SAE J2464, is the crush test. In this test, the cell is radially crushed to 85% of its diameter and held there for 5 minutes. After the 5 minutes is up, the crushing continues until the cell has reached 50% of its initial diameter. The results of this test are similar to the nail penetration test. The cell shorts internally, there is an increase in temperature, but no thermal runaway, no ignition of vapor, and no flame or smoke. This is once again deemed to be a low hazard level. The relatively benign results for these tests stand in stark contrast to those obtained with lithium-ion batteries. Substantial engineering effort and cost is expended in an attempt to minimize the fire risk from damaged lithium-ion batteries. To wrap up, I'd like to spend just a moment describing the Maxwell Ultracapacitor cell product line. Maxwell manufactures cells in 3 product lines. The first line, the standard series, consists of cells from 3 to 540 farad. Most are rated at 2.7 volts, but we have 3.0 volt ratings on select cells in this series. These cells have set the standard for small to medium-sized cells for years. The second line, the XP series, consists of cells from 3 to 50 farads. Each cell in the series is available in either 2.7 or 3 volt ratings. What makes these cells stand apart is that they have improved sealing and other features to extend their life in high heat and high humidity environments. These cells are a natural fit to the harsh environments encountered in automotive applications. The third and final line, the DuraBlue line, builds on over 20 years of Maxwell experience with 60 mm diameter cells. Available in 2.7, 2.85, or 3 volt ratings, with capacitance values from 3,000 to 3,400 farads, these cells set the standard for shock and vibration performance, once again an attractive attribute for automotive application. These 3 tables show the specific cells available in each series. This information is of course available on our website. To conclude, I'd like you to remember the following things from today's talk. First, ultracapacitors have been successfully supplied to the automotive industry for over a decade in multiple applications. Secondly, the increasing electrification of automobiles will provide additional opportunity for ultracapacitors to be applied. And third, with its long history and broad product line, Maxwell is well positioned to be successful in automotive applications going forward. With that, we've reached the end of my presentation. Thank you for your attention, and if you have any questions, feel free to reach out through the websites or email addresses listed here. Thank you again, and goodbye.